Okay, hi everyone. This is important. When does a sequence converge? Okay, so a sequence, and let's just call it z sub n's, where it's understood what I mean is for every natural number little n, we get some number z sub n or z of n. That's a complex number. And so I think of them as a bunch of little dots in the complex numbers. And they might be going somewhere. If they converge, then they actually are going somewhere. Okay, a sequence z sub n converges if there exists some complex number that it converges to. Like if w is there, then all the z sub n's are going to go and get closer and closer to w. So if a sequence converges, first there needs to exist some w. There exists w, its limit, and that's called the limit of the sequence, such that for any desired closeness, little d, a positive number, so like the radius of a ball. Well, now I'm gonna switch and do some pictures, such that for any d, and we have to keep going. We're not done with our precise definition, but I need to think about some pictures before I can finish. So here I am in the complex plane. There exists some number, the limit of the sequence. We would write the z sub n's converge to w, and w is the limit. Okay, but in my picture, here's w. Then maybe here's z1, maybe here's z2, z3, z4, z5, z6, z7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And I cannot finish drawing them because there are infinitely many. There is z 10,428. And the point is, it should be really close to w. So how do I do this in a picture? Well, first I'm just still thinking. For any desired closeness, little d, let's say if little d was 2, d equals 2. Then there's a ball of radius 2 around w. And what I see is that, okay, 1, 2, 3, 4, 5, 6, 7 is outside the ball, but the 8th one, z sub 8, is actually inside a ball of radius d equals 2. Its distance from w, the distance between z8 and w is actually less than 2. And for any of the other zn's, that's also true. So actually, if capital N is 8, then little n past 8 implies that z sub little n minus w is less than 2. In particular, like z9 is less than 2, z10, distance from w is less than 2, z11, distance from w is less than 2. All of them, we could say for all n past 8, zn minus w is less than 2. Okay, but convergence is stricter. It's more. We need more than that. We need it for any distance. So in fact, like I could choose a distance, like let's choose the distance 1/2. I build a little ball of radius 1/2 around w, and now you see that z8 is only there. It's outside that ball. So there needs to be some other cutoff, z9, z10, z11, z12, z13. It looks like 14 is a cutoff. So not n equals 8, but n equals 14. If I choose, if d equals 1/2, then I get the smaller ball. Then I need the cutoff n equals 14. Anything past that, if a little n is greater than or equal to 14, then we have that zn minus w is less than d. Okay, and so that's my picture. And I had to draw that picture to now remember the precise definition. For any desired closeness, there exists a cutoff value. There is some cutoff. There exists some cutoff index, capital N. It's an index, like it's going to be z sub capital N. Like, for example, z sub 14 was worked for when d was 1/2. If I take a smaller d though, like before z8 worked, but now for a smaller d, z14 works. The point is that for any size d, there should be a cutoff where everything past that point is inside a ball. Some cutoff index n such that all the z sub n past z sub capital N, which is sort of such that if little n is past capital N, then, or maybe even for all, let's say it that way, such that for all, we need all the infinite tail. We call this maybe the infinite tail of the sequence, all the z sub n's that are past the cutoff. We have zn minus w less than, for any d, any desired chosen distance. This is the hardest thing to understand, is this definition. So let's put it in formulas. There exists a w such that for all desired closenesses, there is a cutoff index such that for all the indices past the cutoff index, we have z sub n minus w less than d. And this has to be true for all closenesses. And really, this is the precise definition. So we say a sequence z sub n converges to w, or z sub n converges if there exists a w such that for all d, there exists a cutoff index such that for all cutoff indices, for all indices past the cutoff, we are d close. We are d close. Another way to say it is we could say, in symbols, z sub n converges to w if, for all d positive, there exists a cutoff index such that for all indices past the cutoff, we are d close to the limit. Okay, so I guess these are just symbols for the words, the sequence z sub n converges to w. Okay. So really this is sort of A and B, because here I'm using words. Maybe I could add some more words. Both of these are sort of very important. You really need to become okay with all these symbols and to know what they mean. Sort of be able to start from a picture and remember what is the concept you're trying to get at, and then recreate the symbols, but also just look at the symbols and be able to unpack them into a picture. Or unpack them into words. So let's unpack them into words. Very informally, as close as you like to w, for all d positive, as close as you like to w, all the z sub n's will be that close. Well, provided you go past some index. And that index, that cutoff that you have to go that far, it depends on the d you chose. It'll be that close if you go far enough. In the sequence. What's far enough? Well, there exists a cutoff index such that all the indices past that are, in fact, that desired closeness to W. It really requires you to use your own words and pictures and try to come to an understanding of these symbols. Okay, it's your turn. How much can you remember? Quiz yourself. Blank sheet of paper. Your own words. Definitely use some pictures. And then the formulas, they really need to be those formulas so that you can understand sort of the language of math.